Let's start. Okay, welcome everyone to the last GEOTOP-A talk of the year. Well, let me just say that these days there seems to be an indisputable world expert in mass partition problems, and that happens to be our speaker today. So it's my pleasure to introduce Pablo Soberón from City University of New York, who will speak on some of his recent work. As you can see, the title of his talk is Bisecting Masses with Hyperplane Arrangement. So thanks to Pablo and thanks to everyone for coming. Pablo, please.
Well, thank you for the introduction, and thank you to the organizers for the invitation to talk here today. So what I want to talk about is some recent results regarding bisecting masses. What I mean by bisecting masses, it just means splitting into equal pieces or into pieces of the same size using hyperplane arrangements like we see in the picture here. This is part of very recent work with Alfredo Hubard, and it gives me the excuse of talking about the related results to this and some of the motivations. And it's also a good opportunity to talk about this because I still have to sort of figure out in my mind why I think that the methods that we're using actually work, because in some sense, as I will try to explain during the talk, the methods were a bit unexpected for this type of results. So let's start with some motivations and setup for what we were talking about here today. And I want to talk a bit about mass partitions at large, right? So to get an idea of what is the general type of problems we want to be interested in and what kind of tools are usually used to solve them. So let's start with a mass in the plane. And this is just, you can think of this as just a region where we can measure the area. And so we have, for example, these two masses. And it turns out that if we draw a particular straight line, maybe we can split them both exactly by half. So the yellow area on this side and the yellow area on the other side would be exactly the same. I hope you can see my mouse. And the red or pinkish area on this side would also be equal to the red or pinkish area on that side. And this is essentially what we're going to be doing. I'm going to give you some resources in the plane or in RD, and we want to split them into equal pieces simultaneously. And our resources are usually finite measures on the plane. Like here, we usually think about just maybe the integral of a continuous positive function, so that it's if you want to think about it that way. Or they can be finite sets of points, but then it's a very discrete problem where I want the same number of yellow points on one side and the same number of yellow points on the other side. And for the other resource or the other mass, if it's a region like this one, I want the same area, or maybe I want the same measure if it's a measure, or maybe I want the same number of red points if there's also a finite number of points, okay? And these are mostly equivalent problems. We don't have a big difference between problems regarding sets of points and problems regarding measures, because any measure you can approximate it by a finite set of points by just taking sufficiently many random samples, and any finite sets of points you can approximate it by a measure by just taking like disks around each of the points and taking a uniform measure over those sets. So we are basically, we get to choose which kind of resources we want to distribute in the plane. And in terms of the partitions, they can be very simple, like splitting with a straight line. I can have something more complicated. So maybe in this case, I want to split them with a circle. I want the same area inside as the same area outside for each of the, let's say, the yellow area and the pink area. Or I could be splitting into more than two pieces. And maybe I want to split things into 3 equal pieces at the same time. Maybe I want my pieces to be convex. So as we're changing the type of resources, the number of measures or sets of points, and the type of partitions we want to split, we get a very rich and wide family of problems. And these are motivated very naturally by mathematical economics, where we want to just get a distribution of resources. They have applications to computational geometry, and as I'll show later, they have also some motivations on the side of algebraic topology. So we get a lot of things in our pod, and we get to choose what we like about these problems and then focus on the problems that sort of emphasize those facets, those features of the problems. And as I mentioned, we get sort of a topological surprise if you're not familiar with kind of problems, that the methods used to prove mass partition results often come from algebraic topology. So for example, this case here, where if I give you two masses, there's a straight line that cuts them exactly by half. We usually think, we might say that the yellow region is the cheese and the pink region is a ham, and then we have two hungry guests and we want to give them exactly the same amount of cheese and the same amount of ham. So this is what we call the ham sandwich theorem. And it was proven by Banach in 1938. It says that if I give you D mass distributions in OR-D, and here by mass distribution you understand whatever you want in terms of finite sets of points or measures, there exists a single hyperplane that simultaneously halves each of the D masses, right? So each of the mass distributions, I think of it as an ingredient. So the more ingredients you want to split exactly by half, the higher you have to go in the dimension, right? In the plane, you can split ham and cheese. In dimension 3 with a straight cut, you can split ham, cheese, and lettuce, and you can get more complicated sandwiches the higher dimensions you go. And the reason why topology pops in here, so let me give you a bit of an idea. If I'm in OR-D and I want to think about the space of all possible oriented half planes or oriented half spaces, it turns out that we can parameterize the space with a d-dimensional sphere. So for example, in the plane, the set of all half planes would be parameterized by a two-dimensional sphere in R3. And we can make it so that if this point x corresponds to this half plane, then the antipodal point minus x corresponds to the complementary half plane here, right? So we have two different half planes with the same boundary line, and it just depends on whether I'm taking this point x or minus x. And if we do this parameterization, then we get to use the Bourseau-Coulomb theorem that tells us about the zeros of odd maps from d-dimensional spheres to OR-D. So if I give you an odd function, meaning that f of x equals f of minus x, that's continuous, it must always have a zero. And if you've never seen the proof of the ham sandwich theorem, what you basically do is, once you have the sphere parameterizing half planes or half spaces, then I'm going to construct a function that tells me how I'm splitting the measures or the sets of points, right? If I call the green side A and the non-green side B, then I can say, okay, for the first set, how many points do I have on the side A minus how many points I have on side B? For the second set, I do the same thing, and for each of those D sets, right? So when I look at f of minus x, it's the same plane but flipping the sides, which just changes the sign of each of these coordinates, so we get an odd function. A zero of this function, it corresponds to a half plane that's splitting everything perfectly, and so we get the ham sandwich theorem. So basically, once we get to use tools like this Bourseau-Coulomb theorem, we get these more post-fusion results, and we get this very nice connection between these geometric problems and these topological tools. Okay, I won't dive too much into the topology that goes in here, but basically, if you keep going and try to, so if you look at more advanced results in mass partitions, then they always have a topological theorem behind them. And so you have this dictionary or this back and forth between mass partition results and topological results, where if I give you a mass partition problem, you might parameterize the space of partitions in some ways, reduce it to understanding certain functions between some spaces, and maybe get a Bourseau-Coulomb type theorem that tells you whether the partitions you want always exist or not. And sometimes you go back in the other direction, and if you have a nice topological result, maybe finding a mass partition result that uses it, it's a good way to showcase why it's important and why you might want to think about this, or even to come up with more things so maybe there are some mass partition results which motivate the development of these topological tools, okay? So this process is so effective that it's basically the standard approach to solve mass partition problems. It's known as the test map scheme, and there are books dedicated to exactly how we go back and forth. And this, as I mentioned, has motivated significant progress in equivariant topology. Here, the equivariant means that you'll have a group of symmetries in your problem, and you're looking at these functions that preserve these symmetries so that are well behaved with respect to this group actions. In the case of the Borsuk-Ulam theorem, it was this antipodal action on the sphere and this analogous action on RD, where you're just multiplying everything by -1. So you have an action of Z2. But if you go into different problems, then you might have different groups and different related results of this kind. And this is also one of the reasons why, if you think about topological combinatorics, meaning about combinatorial problems that use topological tools in the solutions, mass partitions is usually at the top of the list of nice examples or nice ways to exemplify how you can use topology to solve combinatorial problems. Okay. So let me show you some key examples. So we talked a bit about the ham sandwich theorem. So as I mentioned, this was proven by Banach in 1938. It was published by Steinhaus. He attributes the proof by Banach. Some people also know it as the Stone-Tukey theorem by a publication from 1942, which is the most known reference. And it says that if I give you d mass distributions in a d-dimensional space, then there's a hyperplane simultaneously halving each of the measures. In the plane, it says you have ham and you have cheese. There's a single straight line that cuts both exactly by half. And the topological backbone, as I mentioned, is the Borsuk-Ulam theorem. So what's going on here, as I mentioned, is we have a mass partition result. We have a topological tool behind the curtain that's actually doing all the work. Okay. Another example, which I really like, is known as the necklace splitting problem or necklace splitting theorem. So maybe it's easier to talk about it with a figure. So I'm going to have an open necklace with pearls in it, and we have two thieves that are going to steal this necklace. Okay, and they want to distribute their earnings between them. So what they're going to be doing is they're going to be cutting the necklace into pieces and distributing the pieces to each of them. They don't know which of the kinds of pearls are more valuable, so they want, like, each of the thieves wants the same, like, half of the blue pearls, half of the green pearls, half of the red pearls. And one thing they could do is just make a cut at each point of the necklace, distribute the pearls, and be done with it. But they want to use the minimum number of cuts. So for example, in this case, we could cut it like this. And thief number 1 gets the intervals shaded in blue. Thief number 2 gets the intervals shaded in green. And then they each get exactly 2 red dots, exactly 3 green dots, and exactly 1 blue dot. So they get exactly half of each, and they're happy with these 3 cuts. And what this term tells me is that regardless of how many pearls you have and what order they come in, as long as you have an even number of pearls of each type, you can do something like this with D cuts if you're using D kinds of pearls. So with red, blue, and green, you can always do this with exactly, or at most, 3 cuts, which is, in some, the way I think about this, surprisingly low. And again, this is a mass partition result. There's a topological backbone behind this. There's an original proof by Hobby and Rice in 1965. Then it was rediscovered by Goldberg and West in the 80s. This is the discrete version. Here they prove the continuous version. And again, it's the Borsuk-Ulam theorem. You can actually prove this using the ham sandwich theorem, but there are some direct proofs that just use Borsuk-Ulam directly. Okay, so we get the same topological backbone, a very different problem now in dimension 1. So let's get something a bit more elaborate. Let's use cuts with fixed direction. So before reading this, suppose, for example, in the plane, I have 3 masses, and I want to use cuts, but instead of using a line in any direction, I'm going to use 1 horizontal line and 2 vertical lines. And once you make this cut, I'm going to do a chessboard coloring. So I'm going to color the regions alternatingly black and white. I want the black region to have half the pink, half the yellow, half the green, and the white region to have half of each of the masses, right? Half the yellow, half the pink, half degree. So what I'm telling you is, okay, so if you want to do something like this in any dimension, you're going to choose k directions, and you're going to use n1 hyperplanes orthogonal to v1, n2 hyperplanes orthogonal to v2, up to nk hyperplanes orthogonal to vk. Then, if you take the sum of these numbers, you can always split n masses this way, where you take a partition with hyperplanes with those fixed directions, and you take however many this is telling you, and you can always do this as long as this multinomial coefficient is odd. So we notice, for example, that if k is equal to 1, this is essentially the necklace splitting problem, but we get some more complicated versions here if we increase the value of k. And the topological backbone is a Borsuk-Ulam type theorem, but instead of the domain being a sphere, it's a product of spheres, and now the action it's z2 to the k. So again, when k is equal to 1, this is the Borsuk-Ulam theorem, just like we mentioned for the necklace splitting. But here we get something more interesting. And the reason we start seeing these conditions is for this result to hold, we need this condition to appear here. So the topological tools we're using, the maybe one downside they can have is that they impose conditions on the parameters of the problem. And so we get something like this. This is also a recent result, a somewhat recent, with Roman Karasev, Edgardo Rotan Pensado, and me from 2016. Okay, let's do one more. Maybe now we don't want fixed directions, but we want parallel hyperplanes. We like this idea. So now we'll give you d+1 mass distributions in RD. And instead of looking for one hyperplane, I'm going to look for two of them. And I want the region between them to have half of each of the masses. So we increase the masses from the ham sandwich theorem by 1, but I allow you to take two parallel hyperplanes. And this one, we don't have any conditions on the dimension or the parameters. It's very similar to the ham sandwich theorem in that sense, but the topological tool here is much more interesting. We have a Borsuk-Ulam type theorem where the domain is now a Stiefel manifold. It's just the space of some orthonormal k-frames in RD. I won't go into it because we're not going to be using these tools in the talk, but you can see how things start to escalate in topological complexity. And as the last example, let me show you a conjecture by Langermann. Rather than the conjecture, I'll show you the known cases. So this is a result by Alfredo Hubard and Roman Karasev from 2020. And usually in RD, you can split D measures with one hyperplane. So if you want now n times D measures, I'm going to allow you to use n hyperplanes. They don't have to have any conditions on their directions. And you're going to do a chessboard coloring, where the regions that this splits RD into, you just color them alternatingly black and white. And you want the black region to have half of each measure, and the white region to have exactly half of each measure, okay? And it turns out that you can always do this as long as the dimension is a power of 2. The conjecture by Langermann is this theorem without this condition, okay? So so Roman and Alfredo thought about this, and they could figure out how to prove this for powers of 2. And the topological tool now, it's discrete Morse theory, and the group acting here is a dihedral group with 2n elements, where you have sort of z2 to the n for the idea of like flipping the orientation of each hyperplane, but you also have a symmetric group Sn acting on the space of n hyperplanes by permuting the hyperplanes. So all in all, the symmetries, they make a dihedral group, and then you have to understand the results of equivariant topology related to these group actions. And this is a very interesting approach. But the main idea is that as you're increasing the complexity of your partitions, then you're also increasing the complexity of the topological tools you need. And so it sort of builds, as you build up on one side, you have to build up on the other side, and it creates this nice feature of mass partitions that as you want to get more general and more powerful mass partition results, then you need more general and more powerful topological tools. And so this it's sort of given back and forth between. Now, one thing to note about the examples I've shown here is that all the examples I've shown you are with chessboard partitions, where we're alternating black and white to the regions, using hyperplane arrangements in ORD. So you get a bunch of hyperplanes, and then you take a chessboard partition, and depending on the conditions I imposed on the hyperplane arrangement, maybe you can partition or bisect simultaneously many measures, or maybe few of them, okay? So in general, if I give you just any general arrangement of hyperplanes, maybe some of them are parallel to each other and some are not, then I can always do this alternating black and white partition, because every hyperplane I can, so for example, for this one, I can call this side the positive side and this side the negative side, and I can color something black if it's in an odd number of positive regions, and white if it's an even number of positive regions. So you never get like a 3 cycle of regions, and you can't do a coloring with 2 colors. If it's a hyperplane arrangement, you can always do this with black and white, okay? And if you remember, half spaces in ORD, oriented half spaces, can be parameterized with a sphere of dimension d. So if I give you n hyperplanes and I orient each of them, then I can parameterize this space with a product of n spheres of dimension d. So this is a space of dimension n times d. And if we impose additional conditions, so some hyperplanes are parallel, or they have fixed direction or something like this, then we're just looking at subspaces of this tori, of this products of spheres. Okay, so this is sort of the world we're living in here. And the main result I want to tell you about today is a common generalization of all the examples I've presented so far. So you can expect the notation to become a bit wild. And a bit of the surprise that goes in here is that the proof is non-topological. So there had been some hints that something like this could be done. Patrick Schneider used a similar argument to reprove the known cases of Langermann's conjecture in the plane. But it sort of breaks down this nice story that I've been telling you, where the more advanced mass partition results you want, the more advanced topological tools you are going to need. And then suddenly there's this non-topological approach to them, which goes a bit against this history that I've been telling you since 1938 up to very recently. And before I jump into the main theorem, so I told you that the notation is going to be a bit wild. It involves somehow a condition on Stirling numbers of the second kind. So as a quick refresher, if we don't remember what this is, the Stirling number of the second kind of A and B, this is the number of ways to partition a set with A elements into B non-empty pieces. So S of A1 is equal to 1, because if I want to split a set with A elements into one piece, I'm not splitting anything, there's only one way to do this. If I want to split it into two non-empty pieces, it's 2 to the A minus 1 minus 1. So this is always an odd number if A is at least 2. Okay, so this is a couple of things to remember. So let's talk a bit about the space of partitions that I want to talk about. And what I want is, I mentioned, I want a result that generalizes all the partitions, all the examples we've talked about so far. So I want a space of partition that I can restrict to each of the examples I have been talking about. So what I'm going to do first is I'm going to give you a number k1, and I'm going to take k1 hyperplanes which are parallel to each other. And I'm going to, so they all have a common normal vector. The normal vector should be in some fixed space L1. Okay, so if L1 is ORD, I'm not imposing any conditions on their direction. If L1 is a one-dimensional space, then they all have this fixed direction. They're all but I could also take things between them. And then I'm going to take K2 parallel hyperplanes for some other K2. And maybe I have a second space L2 that's telling me where this normal vector can live. And I do this with K3 and K4 up to Kn. Okay. So as I am fixing the values of K1, K2 up to Kn, or the value even as I'm taking the value of n of all the numbers k1, k2 up to kn, and all the subspaces L1, L2 up to Ln, I can get a lot of these very different spaces of partitions. So, and finally, we take a chessboard coloring that I said, if we have a hyperplane arrangement, we can always color the regions of RD black and white alternatingly. So for example, if n is equal to 1 and k1 is 1 and L1 is RD, meaning I have only one hyperplane, I'm not imposing any condition on this, this is the kind of partition or the kind of partitions I'm looking for the Ham-Sandwich theorem, just a single hyperplane in any direction. If n1 is 1, now k1 can be any number. Oh, I'm sorry, k1 is 2. It's the only make I change. Then we get two hyperplanes and they can be in any direction. This is the kind of results that I showed with Yuki Takahashi. If the dimension is 1, if D is 1, and we don't, so here L1 is also R1. Now K1 could be any number we want. This is the necklace splitting theorem, or the necklace splitting cuts with the K1 cuts, right? If all these spaces I mentioned here have dimension 1, meaning that all the normal vectors that I'm imposing, they always have to be in a fixed direction. This is the kind of partitions that we talked about for fixed directions of hyperplanes, the one with Edgardo Roldan Pensado and Roman Karasiov. If all the K1s, K1, K2 up to Kn, all of those are equal to 1, and all the spaces here, L1 up to Ln, are all equal to RD, then we just have n hyperplanes without any condition on them. This is the kind of partitions that the Langermann conjecture uses. So you can see that this very general space of partitions, as we're choosing the parameters, we can restrict it to each of the examples we had before. Okay, so now I'm going to throw in the main result on the screen, and it tells us that in the space of partitions I described, so you have your n and d, you have your subspaces describing the directions of dimension Li, as a dimension of the spaces, and the number of hyperplanes in this case. So if I define this number mi, then when I take the sum of these things, if I take any m mass distribution in RD, then there's a partition of the kind I told you about. This is just this big paragraph here that bisects each of the masses. Okay? And in each of the examples I told you about, if you want to recover them with this here, the number of masses that you get here, you can trust me that you get exactly the same number of masses as in the classic theorem. And whenever I say you should trust me, or trust me that this happens, you should not trust me, and just double check it, but you get the exact same number of masses as before, with all these restrictions that we had, which is essentially the dimension of the corresponding space of partitions. And the elephant in the room is that we need this strong condition here, this strong number here, to be an odd number. Now, when k1 up to kn, if these numbers are equal to 1, here these string numbers are equal to 1, so it shows why we don't have things appearing if, like in the Ham-Sandwich theorem or the result with Takahashi about parallel hyperplanes. In the case of hyperplanes with fixed directions, there was a multinomial coefficient. That's a multinomial coefficient that sort of appears here. And in combinations of those, you have combinations of those things. In the Takahashi result, where we had two parallel hyperplanes, we also had this Stirling numbers here, which is always odd if k1 is equal to 2. And then we have some group here that lets us sort of reduce these things. I won't go into details of why that's the case, but sometimes we get to divide by something here, and then that makes things more likely to be odd in this scenario here. Okay, so I really don't like having a slide of only text, but I wanted to showcase like the big theorem that sort of combines all the previous cases. And it in addition to giving us like recovering all the previous results we had with the exact same number conditions for like the fixed hyperplanes and the Langermann conjecture. We had this conjecture in the paper where we proved the result about two parallel hyperplanes. That if I want to give you d plus k minus 1 mass distributions in RD, there should always be k parallel hyperplanes, so that if you do the chessboard coloring, I'm going to halve each of the masses simultaneously. So when k is equal to 1, this is the Ham-Sandwich theorem. When k is equal to 2, this is the result I told you about with Takahashi. And we can adapt this result here to this thing. And what it tells us is that the conjecture is true when this is an odd number, which I think it's really surprising. We don't know if this is actually necessary. I'll talk about more about the necessity of these conditions at the end of the talk. But as I mentioned, this main result has a non-topological proof, right? Now, all the cases that we could recover and that we knew about, they all had known topological proofs. And this is sort of a new one that we get as a corollary from this big result, that we only knew the non-topological proof for something like this. So there was some pressure to revisit this conjecture and see if we could like tackle this in general. And that's something I did recently with Nicolas Sadovec. And we used the Fadel-Hosseini index and more advanced topological tools to try to tackle this, a very different way of parameterizing the space of partitions and seeing what kind of maps would imply that a zero means you have a bisection of these masses. And somehow we could, with completely different methods, reprove this corollary exactly, where this condition of the Stirling number appeared again by itself, which I find really weird. It might be pointing out that this kind of conditions is actually necessary, and I will go back to this towards the end of the talk. Okay, so proving the main theorem. The main theorem, as you notice, like just having it in a slide, it's like not the nicest thing to have because it has so many notation and so many moving parts. So instead of trying to convince you that this is true and what are the main ideas of the proof, I want to look at the proof over that theorem in two particular cases. One is what happens with the Ham-Sandwich theorem, and the other one with the Nekla splitting theorem. Because all the nuances, or almost all the nuances and weird things that happen in the proof of the big result with all these notations is it's really going to be reflected here and here. And if I can convince you that these two things have a non-topological proof, then maybe you'll be convinced to look at that paper and see if that actually works in general. But what I claim is that once you know what happens here and here, there are almost no surprises in the general case. Okay, so let's go and revisit the Ham-Sandwich theorem. So what happens here? We have, so what I want to prove is, for example, in the plane, that if I give you any two set masses, there's a line bisecting each of them. Or in RD, if I give you d masses, there should be a hyperplane bisecting each of them. The first thing I'm going to do is, so usually for the topological proofs, we want measures which are absolutely continuous with respect to the Lebesgue measure, right? We want the functions we construct to be continuous, and so smoothness in our resources is something very important. Here we're going to do the opposite thing, and we're going to make our resources finite sets of points. We said that there was no issue with doing this at the beginning of the talk, and I'm going to go one step further and ask that the number of yellow points is an odd number, and the number of red points, or I guess brownish points, is also an odd number. Okay. And again, there's no loss of generality of assuming this. And the thing is that if, say, I give you a bunch of points in general position and there's an odd number of them, a line that's bisecting them in the plane necessarily has to go through one of them and leave the same number of points on the two sides. If it doesn't go through one of them, then since it's an odd number, you can't have the two sides match on the same on the number of points. So if I give you, maybe it's easier with a figure here. If I gave you a line that was bisecting the blue points and the red points, it has to go through at least one blue point. It has to go through at least one red point. So it has to go through a blue-red pair. and since we have a finite number of blue points and a finite number of red points, there's a finite number of candidates for this line to be the halving, or to be a halving line. And what I claim is that once you establish that you have a finite number of such candidates, the number of, I'll talk about things in the plane, but this works exactly the same thing in high dimensions. The number of lines that simultaneously bisect the blue and the red points, I claim that it's always going to be an odd number if the points are in general position. And since 0 is not an odd number, then there has to be at least one bisecting line. So if I could convince you of this, that the number of halving lines, which is now a finite, there's a finite number of candidates, is odd, then we would be done, and we would have a proof of the ham sandwich theorem. And what we're going to be doing is, I'm going to start with a configuration of points, and I'm going to take one of the points and start to move it continuously, okay? And at each point, there's a finite number of halving lines. So if I move my points continuously, I'm going to show that the parity of halving lines never changes. So if at some point I can figure out a special configuration where there's an odd number of halving lines, then in any other configuration, by doing this moving point argument, if you believe me about this invariant, then we would always get an odd number of halving lines, okay? So this is what I want to convince you here. And the thing is that if my points are well separated, so maybe my blue points are very far away to the left and the red points are very far away to the right, all the lines that go through a blue point and a red point are mostly horizontal. So if I look at the points, the blue points from top to bottom, a halving line that's mostly horizontal has to go through the middle point in y coordinate, and it has to go through the middle point here in y coordinate. So there's exactly one halving line if the points are concentrated and far enough apart, okay? So we do have configurations where there's exactly one halving line, and so if we get this moving point argument to work, we would get this to work in full generality and get the ham sandwich theorem. And this, you can, I'm talking about things here in the plane with two colors, but everything I'm telling you about, it works in high dimensions with almost no changes. Okay, so suppose I give you I'm moving my points continuously, and you have this pair, a red point and a blue point, AB, that's representing a bisecting line, and that at some time t, it stops being bisecting. So what happens if we have a change, like we have this bisecting line, and the only way it can stop being bisecting is if the moving point goes through this line, or maybe A is the moving point, and that forces like the line to go through one of the points. It's exactly the same thing if one of the 2 points is the moving point, or if it's a moving point going through the line. But you have this crossing here. So since we have already a red point and a blue point, maybe the crossing point is red. Let's look at that case. And so we have this point A prime, which at time t minus epsilon, it's on one side. At time t, it goes exactly through the line. And at time t plus epsilon, it's on the other side. So what happened here? What I'm going to be looking is, what if we replace A by A prime? So I have this other candidate line here. And this other candidate line, as it was moving, notice that on t minus epsilon, it had A on this side. Then we have at t, it coincides, so it has A. And at t plus epsilon, now it has A on the other side. And if epsilon is tiny enough, then A is going to be the only point that crosses this dotted line here. So we have this exact one change. Now, the cool feature about this is that the line A was halving at t minus epsilon, right? So at this moment, we have the same number of red points here and the same number of red points here. And now here, since this A prime crossed, it's almost halving. We have one fewer point on this side, red point on this side, and then red points on this side. Here we have the same number of blue points as the number of blue points here. So A prime is also almost halving at this point because it's the same line. It has the same number of blue points on each side, and the red points, it's off by 1. But we know that from t minus epsilon to t plus epsilon, the point A is changing sides here. So the only way that can happen is if it was balanced before and unbalanced after, or unbalanced before and balanced after. So we get this. I'm going to write yes if the line is corresponding to the pair is bisecting and no if it isn't. So we go from yes to no on pair A, and for pair A prime, we have it either goes from no to yes or from yes to no. In this case, the number of halving lines stayed constant. We lost 1 and we gained 1. In this case, it got reduced by 2. And whenever you do this, there's exactly one pair, like other candidate A prime for this A. So the number of lines is always changing by 2. This is the analysis when a line stops being bisecting. When a line suddenly starts being bisecting, it's the exact same argument. It's even like this. You can think about the time going in reverse, and it will be exactly the same analysis. So what we get is this change going by 2 every time, and that preserves the parity. We had an initial configuration with exactly one halving line, and so we always have an odd number of halving lines. And again, I did not use Borsuk-Ulam so far, right? So this would be a mostly complete proof of the Ham-Sandwich theorem. You just have to fill in the gaps for every time I told you to trust me, and hopefully that works out all right. Okay. So what happens in the other cases? Let's look at the necklace splitting theorem, because it's almost the same story. So now we have odd sets in OR. Now, if I want to split the green points, one of the cuts must be at a green point. If I want to split evenly the red points, at least one cut must be on the red points, and the same thing for the blue. If I'm only using 3 cuts, one must be at a blue point, one must be at a green point, one must be at a red point. Okay, so we have one cut in each of these colors. So the number of we're basically counting triples of rainbow colors and looking if the cuts at those 3 points would give me a good bisection of the necklace. And what I want to show is that the number of halving rainbow cuts is always going to be odd. And we're going to be doing the same thing as before, where we're going to be moving the point continuously. And we always have a configuration where there's exactly one good cut, because if I have all the red points first, then all the blue points, and then all the green points, the only bisecting cut for each of them is when we have the middle point for each of the colors. So we have an initial configuration with exactly one bisecting rainbow cut. And we want to see that as we move our points continuously, the number of cuts is 6 here. Okay, so suppose now I have a rainbow triple that's bisecting A, B, C, and the only way it can stop being bisecting is if one point crosses one of the cuts, or the crossing point moves and then crosses another one, which is the same thing. So if we had, for example, a red point crossing the red cut, we can start with this A and then look at this triple A prime, and the same analysis we did in the ham sandwich case works here, right? So the main idea is that if I give you this triple A, I want to be able to construct this alternative triple A prime where it's also changing at that exact same moment, whether it is bisecting to non-bisecting or non-bisecting to bisecting, and then the parity, they either both stop being bisecting or one started and one stopped. Okay. Now the issue here is that, well, this was very convenient that this was a red point crossing the red cut, but what if it's a blue point? Then if I want to do this this exchange of changing A by the point that's crossing here, B prime, now the triple B prime BC is not a rainbow color, yeah, right? I don't have a red point in this triple, which is sort of an issue, in this case. So what I'm going to be doing is at this time t, I'm going to be adjusting the cuts, and I'm going to be, so I have too many blue points, So I'm going to take the blue cut and move it to the left, right? Because this blue point, it was on the black region. So it means that the black region is losing a blue point. So here I'm moving it to the left so that this starts being on the black region. And so I still keep the blues balanced. And we're going to move this cut at B until we hit a new point, X. Now, if X is red, then we can take the triple X, B prime C. So we have this point here, this point, and this point, and do the same analysis as we did before. We have an issue at time t when we have this crossing and there's a non-balancing and it all works exactly as you expected. If this X is blue, then we take the pair AXC and it's the same analysis as before. And if X is neither this color, so in this case it would have to be green, then we have in X, B prime C, we have two green points. So we're going to be moving this cut here. So at any point, we're going to try to figure out if we can get this updated A prime to be able to do the analysis we did before. And if not, then we're changing the cuts a bit to figure out a new thing here. And for example, here, the black region is losing, I'm sorry, the white region was losing a green point. So this should be moving to be in the white region. So this should be moving to the left. And so every time we're doing this, we know which cut we have to be changing and in which direction we have to be moving it. So the idea is the main goal is to start with A and end up with some A prime so that one of these 2 points is one of these 2 points so that we have the issue at time t. And we want also our cut to be almost bisecting each of the colors, okay? Bisecting all of them except one, which is almost bisecting. And so we start doing this game of like, we try to replace something here. If it doesn't work, then we have an overloaded color. We make a change on the cut. We look at this one. Is this the one we wanted? If not, then we know what to change and we keep updating our candidate for A prime. And this is a deterministic shifting process. Now, what I claim is that it's impossible to run into a loop. And the reason why that happens is if we started with our triple A and we start doing this process of updating or things and we start running to a loop, the fact that it's deterministic, it means that we can also do it in reverse. And if we were in this loop here and we started running in reverse, on one hand, we should also stay on the loop going backwards, but we should also come back to A because we're undoing everything we did. Since those two things are incompatible, it means that as you're doing this process, you must end up with some A prime at the end. And the only way to get stuck is by getting one of the candidates that did exactly what we wanted at the beginning. So you get this updating thing here. But the main idea was to try to replicate what happened with the Hamzani theorem, where we had started with a cutting tuple A, and we want a cutting tuple A prime, and they either both stop by being bisecting, or they both start being bisecting, or one stops and one starts, and so the property of bisecting tuples doesn't change. And in general, there are two update rules. I won't talk about the other one. There's this translation rule that I told you about with things on the same group of parallel hyperplanes. We can also slightly rotate the directions of the hyperplanes if we have this freedom. If some other things happen, in the cases where that's a possibility, and you can analyze those cases and basically get this updating rule change in the very general case. And the reason why we had this condition on the parameters on the main theorem is because we can get a configuration with exactly this many bisecting tuples of hyperplanes with this horrible number of conditions. So if this is an odd number, we have an initial configuration with an odd number of cuts. If we believe in this process here, it tells us that the pairs that start being bisecting or stops being bisecting, they come in like we either have two appearing or two disappearing or one appearing and one disappearing. And so it means that as long as this number was odd, then for any set of resources, we can always get this bisecting cuts here. Now, one question is, okay, this method works, or this condition is actually necessary? And we have some examples where they are, but in full generality, we actually don't know. So the first case we don't actually know what's going on is what I would call the tic-tac-toe partitions. So now I'll give you 4 mass distributions on the plane. And the question is, can we always find 2 vertical lines and 2 horizontal lines that, when you do the chessboard coloring, they bisect each of the 4 masses? I call this the tic-tac-toe partitions. And if you run this with our big theorem, the condition that we want to check that it's odd, in this case, it's even. So our methods don't tell us anything about this. So the number of bisecting tuples should always be an even number, and we don't know if we can avoid 0 among those even numbers here. But this is like a very down-to-earth problem in the plane that maybe if this happens to be solved, like if the answer is positive here, we might be learning what is missing in this main theorem. And if the answer is negative here, I would be very inclined to think that maybe this condition is actually necessary. And the other version is, well, what about Langevin-Mann's conjecture? I would actually venture to think that this is, that the known cases maybe are the only ones which are true. When the dimension is power of 2, or when the number of hyperplanes is 1, that's when you get the Ham-Sandwich theorem. So the first case we don't know about is dimension 3 with 2 planes. So if I give you 6 mass distributions on R3, is it possible to find 6 mass distributions so that there are no 2 planes whose chessboard coloring bisects each of the masses simultaneously? And I think that's as far as I wanted to get to today. So thank you very much to the organizers again, and to everyone that's here. I'm just leaving here the archive references for the papers if anyone is interested in them.
Okay. Thank you. Is my microphone on?
Yes.
Thank you. Thanks to Pablo. Thanks a lot. Are there any questions? So okay, I'm not sure. I don't see any raised hands. Are there any?
Sorry, I forgot how to raise my hand, but I do have a question.
Please.
There we go.
Yes, please.
Yeah. So I didn't understand one thing about the argument for the necklace case, that you show that you can't fall into a loop, but that argument you gave doesn't seem to discard if the whole thing is a single loop without any tail at the beginning. Right? So the argument was you can go backwards and forwards in a unique way. So then you can't have 2 arrows meeting at one point. But what if the whole thing is a single loop?
What if the whole thing is a single loop? We have arguments for that in the paper, but it's when you it basically comes from the fact that this that the direction in which you're crossing is given, so it gives you just one neighbor for this. That's what implies basically that you have one neighbor for the initial thing here.
I see. Mm-hmm. Okay, thank you. Yeah.
Okay. I don't know if there are more questions. I have a question. Could you please put back your main theorem, Pablo? Yeah. So as when I was looking at the where the parity condition comes in your in your arguments, in your proof, well, in your sketch of proof for the cases you showed, I was precisely wondering if you knew that the parity condition here was necessary, but then you let me try to make sure this is not a very stupid question. Okay, if it's stupid, that's fine. You don't know if this is necessary, right? I mean, you do have some examples in which this is not satisfied and the theorem doesn't hold, right?
Yes, so those examples, let me see if I can go back to the initial examples. We have here quite a few slides. Let me go back to the... So in this case here, in this case, in the original paper with Roman and Edgardo, we show that this case with one vertical line and one horizontal line is then it would give you an even number here, and that one we have a counterexample for. And then with Alfredo Hubard, we revisited those examples, and then this condition basically here, it's telling you that if you look at the numbers n1, n2 up to nk, then when you write them in base 2, they don't share a 1 in any position. And we could improve the counterexample with Edgardo and Roman to say that if here I have 2 odd numbers, then we have this is going to be even, and we have a counterexample for this. But that's the only cases where we have counterexamples.
Okay.
Yeah. So this is why I'm interested in those tic-tac-toe partitions, because this is even in the case with fixed directions, that's the first kind. Because what you're looking for is if they have a 1 in, when you write them in binary, in base 2, if they have a 1 in some position, and we could say, okay, if you have in the units 2 1s, then we have a counterexample. So the tic-tac-toe is when you have 2 1s in the next position. And maybe that one is the next counterexample. That's the next easiest counterexample to construct if it exists.
I see. Oh, I see. Okay. Now it's very clear. Okay. Wow. Okay. That's very impressive. Thank you. I think Gilberto Calvillo. Gilberto has a question, please.
Yes, I have a question. Well, a couple of questions. In the I don't know very well the proof of the Borsuk-Ulam theorem, but I think that it is it is not constructive. It is existential only. And the proof that you are given now, it is a constructive proof, right?
Yeah, so this is sort of telling you the complexity class that this problems are in, if you look at this from the point of view of computational complexity. And this path searching arguments, whenever you can solve a problem like this, the complexity class is called PPAD, path parity. And it's telling you a bit about this kind of result, like what is the computational complexity of this thing. That had already been proven for, say, the necklace splitting problem, and I think for the I believe that also for the ham sandwich theorem by other means, but this is showing that like anything that you can fit into this big theorem is also in this PPAD complexity class. In terms of like the computational complexity of solving for this partitions.
Okay. Well, my second question is, how essential is this parity condition that you have in all these theorems? I think you addressed that at the end, but I didn't understand very well.
So if I wanted to make a wild conjecture, it would be that this is always necessary for this to be true. I'm more inclined to think that this is necessary since we have these weird little examples where it starts to become necessary, and the fact that for the conjecture that I had with Yuki Takahashi, if we try to address it with other methods, we got exactly this same Stirling numbers condition appearing. So I would venture to think that maybe this is actually necessary, but this is, I wouldn't put my hand on fire over this.
Okay. Thank you.
Thank you. Okay, it's 11 already. Any other question? Okay, if there are no more questions, then let me thank again Pablo for a really nice talk. Thank you very much, Pablo. Thanks everyone for coming.
Thank you.
Thank you.